Hi, this is a demonstration for the Iris 9000 Plus. So the first steps would be to set up, get your probe turning, getting everything ready to go. Next thing you do is build an inspection map of the exchanger you're going to inspect. We just built a small thing here. Then you would mark tubes you can or you don't have to, but we usually mark the tubes we're going to inspect for a plan. You can just build the plan as you go. It's just one extra step. You'll have to, each time you click on a tube, it'll ask, do you want to add this one to the plan? So click on a tube. We're going to pull a C-scan and record. You can go, this is B-scan mode. You can record a C-scan if you like, and even from this mode without seeing the C-scan. And real quick, I'll show you something. If you want to move it to the 4 defects, different sizes. Those are all defects right there. So the iris automatically reads what it thinks the smallest defect is, the thinnest point, and that's a 38 thousandths. But with the red cursor, you can move. That's a 38%. I'm sorry. Then this is a 67%er. This is a 82%. And then iris is always reported in remaining wall. This is a 51%er. So you can read each point. This is a donut shape. So if I was to put it on this screen, you can see this is one slice of the tube. And these cursor all corresponds. These grid lines correspond to this. This 90 corresponds to this 90. 180 to this 180. So when you're looking at this B-scan, you're looking at one slice of the tube in one spot. So now you can, by the way, you can load defaults, which would be for the tube that comes with the system, the copper nickel tube that we send out with the system. And that would just be so you can verify is the system still working based on the factory settings when it left our shop to come to you. You can save as many configurations. This is all, the configurations are all these settings on the left side, on the right side of the screen, I'm sorry. So you can save the material, you can save different size tubes, 1-inch tubes, 2-inch tubes, carbon steel, whatever material. You set your settings the way you would prefer them. You save that configuration. When you come back to do that tube, you would click load configuration, find it, load it up. You'll usually have to tweak it a little bit, but it gives you an excellent starting position. So go back to the end, James, and we'll pull a C-scan, record a C-scan. Oh, one thing before we start that, get back on the screen. So we have these RPMs down here. This is typically the speed we run, about 4,000 RPMs, 4,000 something RPMs. Turn it down. For if you're going to pull like 100 inches a minute, a slower speed, you can do that. You want to be above 2,000. You can be anywhere above 2,000 up to 11,000. Is excellent. The faster you are, the faster you can pull the probe through the tube. We find that the about 4,000 gives us the best images with not lots of extra readings, so we get a more profiled image. Turn back up. You can go back up to see if it'll go up to 6 or 7 or how high it'll go. 6,000. So as you see, the image did not change. We adjusted the RPMs down here. The image never changed its speed or it changed its speed, but it never changed how steady and how synced it is. All right, go back to the end, put it back on where you want to be, and it's on 5. Is that where you want to be? All right, so go to the end. Now you're at the end. All right, we're going to acquire a C-scan, start pulling. You can see it loading on this screen. This is for your review to make sure you're getting good data. The actual data is getting stored in the background. for you to use and build reports. Yeah, Dan? Okay. I'm going to stop the recording. You enter in, you make, if this isn't correct, you change it. It's your starting position, your end position. How much length of that tube you record it. This is only a 2-foot long test tube that we use here. We save it, go to the map, right click on the map on the defect, and then you can see, if you look at the top section, this is called a longitudinal V-scan. This one shows you a taper on the OD. So the bottom side is ID, the top side is OD. That's the OD defect, OD groove, OD notch, OD pitting, OD pitting, OD pit, through wall hole, ID corrosion. Okay. If you move your cursor either here or here, you can see the right-hand side of the image comes in. That means it's OD. And over here, the left side of the image comes in. That means it's ID. You have a through wall hole with a small ID pit drilled on the opposite side. You have a notch. One thing you can do with here, you can set your cursor to wherever you're at. That's 74% of nominal wall. That is 11% of the circumference of the tube. We can mark, oh, by the way, we can zoom in on the actual defect. We can mark a B scan. We'll mark a C scan. You can do either or both. It does, whichever you prefer. We'll go to info. We're going to say that that's we'll just say OD notch. So we do have these other ones that you can pick from a list, or you can type in your own. Then we can add a report line. This one we're going to just say is external corrosion. Create. And anywhere, by the way, anywhere you move this cursor, this is what you're seeing, the B scan that corresponds to the C scan you're seeing. This is in my way. We go to reports, you'll see we have a report line entered in there. Side view, this shows where that defect is located, and the color code says it's 79%. This other tube, the first tube, shows that's 40 to 49%. You can put supports on here. You can just draw them. Edit list, you type them in actually. Add a new, let's say it's at 1 inch. 2. Oh wait, that's -2. -2. 2. -2. 2 inches. And say okay. So it'll add supports for you wherever they're located. You can go to the print tab then. You got a cover that shows information about the job that you set up, a summary, and on this summary you can write down, you know, how many tubes you inspected, how many had this defect, how many had that defect, how many in this percentage, any other information you want to convey to the customer. We have a map that's by wall remaining that shows the color codes correspond. again by a map, same map, but by damage type. So it shows whether you have internal pitting, external corrosion, whatever you report it. Same two maps in icons. The side view that we made shows 0 foot, 2 foot. This defect was just under 1 foot. Report lines.
I'd probably go with that then.
The inspection information, but the inspector information, you would complete this. The B scans, this is a B scan I did earlier at the top. This B scan is the one we just made. And it shows you that that's an OD notch. It was tube A2, 11% of circumference at 11 foot 3 inches, and it was 52 thousandths remaining. By the way, we're working in inches, imperial here, because that's what we're used to, but the system does metric same way. It's just one click of a button in the setup screen. I'll show you that in a second. Scans. This is a C scan we did earlier. This is a recorded C scan we just did just now. Again, color codes for the matching colors in the C scan. We assigned the B scan that we wanted to show you. And then a blank map just with no data, so the customer can go back in the future and mark up these tubes. You can also very easily make a tube map for the customer if you like. The way you set up for metric is in the edit info. I can just go in here and say metric instead. Okay. And then when I come back out and go to print, these readings should be in metric, and the B scan should be in metric, and the C scan should be in metric readings right here. So the other thing you can do in setup is if we have a list of materials. Let me show you the list of materials first. So a long list of different known velocities. That's how you calibrate. The known velocity for the copper nickel 9010 is 5,007 meters per second. For say carbon steel, which is it doesn't really matter whether it's 214 or 179. Steel carbon is always 5,930 meters per second. But let's say you come into a material that's not in that list. If you know the velocity, you add the name and the velocity, and it would be in the list. Let's say 620, create. Then if you notice that image in the background calibrates, let's go back to something that's quite a bit different. 10, you see how thin the image is? Go to the test one I just made, and it calibrates to that material. So it's self-calibrating system. One other thing about this system that no other system does, as far as we know, is with every pulse we send out, the electronics automatically self-checks calibration with every pulse that's sent out. So I think that is a quick demo. If you have questions, get back with us and we will be happy to answer them and help you out. Thank you.